Hello everyone, I'm Youyou from Tsinghua University. I'm very glad to introduce my colleague Shiwei's work, Weaver, Efficient Multi-LLM Serving with Attention Offloading. Let's start with the background and motivation. We observe two trends for LLM usage today. First, model-as-a-service platforms like Together.ai serve hundreds of diverse models. Second, large companies like OpenAI are deploying tens of specialized in-house models. The common trend is clear. Serving multiple LLMs concurrently is a mainstream deployment requirement. A key characteristic of these multi-LLM workloads is a highly skilled workload. We confirm this by analyzing production traces from OpenRouter, a large model-as-a-service serving platform. As the CDF plot shows, the demand is far from uniform. The top 5% of models account for nearly 75% of the token workload. That means several hot models receive a large percentage of the requests, and many more cold models receive a small portion. This extreme imbalance between hot and cold models is the central challenge we must address for efficient serving. So, how is the problem handled today? Existing methods fall short. The first solution is simple: dedicated serving, which deploys the hot and cold model on separate GPUs. It can waste significant GPU memory on underutilized cold models. The second solution is model parallelism, like tensor parallelism, which improves memory usage by collocating multiple models on the same GPU. But it requires inter-GPU communication, like all-reduce, and introduces significant performance overhead. This presents a difficult trade-off, leading to our design goal. How can we maximize GPU memory utilization without sacrificing performance? Next, I'll introduce the opportunities and challenges for multi-LLM serving. Let's first review the computation process of attention. In attention computation, the QKV of the current token is the input. The Q first product with history KV cache and get the attention score. The attention score is used to dot product with the V vector of the final output. So, in decode attention, only the QKVO vector of the new token is needed. By using this computation feature, many existing works proposes attention offloading. The idea is to offload the expensive attention computation from a busy GPU to another devices like CSD or PIM. Only QKVO vector needs to be exchanged between GPU and the secondary device. When adopting this idea to the GPU, it allows a hot model to borrow spare memory capacity from a cold model's GPU. Crucially, this can balance memory utilization across GPUs with small communication overhead. However, this introduces a new critical problem. Unlike offloading to the dedicated hardware like PIM, our offloading target, the cold model's GPU, is not idle. It's actively running its own inference tasks. As the timeline shows, when the sender offloads a task, it gets stuck in the receiver's command queue, waiting for the cold model's local kernels to finish. The core issue is that the target is not dedicated. Offloading tasks can be blocked by the receiver's running code model. Let's dive deeper into this blocking problem. The first challenge is blocking by pre-issued kernels or head-of-line blocking. Modern inference engines like VLM asynchronously issue many kernels to maximize GPU utilization. This means our high-priority offloaded task arrives and finds a long queue of kernels of the code model. It causes a significant and unpredictable delay. The second challenge is being blocked by a single, long-running kernel. Even if the queue is short, if the receiver is executing a single large kernel, like the final LM head projection, our offloaded task must wait for its entire duration. This single kernel can also become a major bottleneck. Next is how Weaver solved the mentioned challenges before. To overcome the challenges we have discussed, our approach is twofold. First, to handle the queue of pre-issued kernels, we introduce a GPU-driven control flow. This involves inserting lightweight polling checks after each kernel. Second, to deal with long-running kernels, we propose operator splitting. We break large kernels into smaller pieces. Together, these techniques allow us to achieve our goal, non-blocking attention offloading. The first solution is a GPU-driven control flow, which creates a low-latency communication path that entirely bypasses the CPU. Here is how it works. First, the sender writes the QKV data to a shared memory region and automatically updates a task counter. Second, on the receiver, we insert lightweight polling kernels into its execution stream. These polls check the task counter. This is the key to bypass the host-side command queue. When a poll decides a new task, it immediately executes the offloaded attention computation. Finally, the receiver updates a completion counter, signaling the sender that the result is ready. This entire loop bypasses the CPU and ensures the offloaded task is blocked by at most one running kernel. Our GPU-driven control flow works well, but it's still possible to be blocked by a single long-running kernel, as we see in this left timeline. So, our second solution is operator splitting. The idea is simple. We break these large kernels into smaller pieces. To formally solve the problem, we observe that a kernel's impact on waiting time is quadratic. This means one very long kernel hurts latency much more than several shorter ones. So, we greedily handle the large operators in this model. The first step of our algorithm is to sort all operators by their running time in the priority queue. So, we can easily find the longest one. Then, we take the biggest operator from the queue, split it into two halves, and insert these two smaller pieces back into the queue. We repeatedly split the new longest operator in the queue, and continue this process until the estimated waiting time drops below a predefined threshold. With operator splitting, our pooling mechanism gets more frequent opportunities to run. Next is the evaluation of our system, Waiver. We compare Waiver against 3 baselines, dedicated serving with VLM and 2 versions of MaxServe, a SOTA multi-LLM serving system. Our testbed includes high-end A100 with NVLink and L40S GPUs with PCIe, feature different interconnect speeds. We use 2 representative real-world workloads, BurstGPT and Azure Conversation. Here are our main results. Waiver, shown in purple, significantly outperforms the baselines. On the A100, we achieve up to 1.22 times higher throughput. The improvement is even more dramatic on the L40S with smaller PCIe interconnect bandwidth, reaching 1.77 times. This is because Waiver's attention offloading requires less communication bandwidth than MaxServe's tensor parallelism. Importantly, the benefit to the hot model comes at a very low cost. The cold model experiences only a minor 3 to 5 millisecond TPOT overhead. We also analyze the Waiver's sensitivity to workload skew. We vary the request ratio between the hot and cold models from a highly skewed 10:1 to a more balanced 2:1. The results show that Waiver consistently delivers benefits across all ratios, maintaining roughly a 15% lower TPOT compared to the next best system. This demonstrates the robustness of our approach. Now here is the conclusion. We propose Waiver, an efficient multi-LLM serving system with attention offloading. It mainly targets skilled multi-LLM workloads. Our key idea is to offload attention from hot to cold instances. Our system has 2 key techniques, GPU-driven control flow and operator splitting. By applying these techniques, our serving system has a higher throughput for the hot model with only a small overhead on the cold model. That's all. I'm welcoming any questions, or you can directly send email to the original author, Shiwei Gao. Thank you.